Hey guys, welcome back to another episode of Simuleo. So this is kind of weird. It's actually work time for me here at OIST. And I don't normally do a stream during this time, but I kind of thought, because we've been doing streaming for so long and, it'd be nice to show you guys what I'm doing actually during work. More than that, there's this one problem I just can't for the life of me solve in my code base at work. So I figure, hey, why don't we just stream it? Maybe someone can help me out with it and we can kind of start working things out. I don't know. So we'll see how this goes. So if you guys don't know, the code base that I work on for work is called GPUE. Let me just go ahead and go to github.com. Let's see. One second. Let it load. Algorithm archive GPUE. So it is a GPU-based Gross-Pdevsky equation solver. You can find more information here on the documentation site. The idea here is that we're simulating superfluids on GPU systems using the split operator method. Now, we've definitely covered the split operator method before on the algorithm archive. If you guys don't know, the split operator method is basically a method that allows for us to simulate, in this case, a Schrodinger equation just by flipping back and forth between real space and momentum space, or position space and momentum space. So basically, we take some sort of quantum wave function, we multiply it by some position, we Fourier transform forward, multiply by some momentum operator, then inverse Fourier transform back and multiply by a position operator. And in this way, we can kind of apply one time step to our system, and that time step is applied via the Hamiltonian. And this is kind of what we'll be working on today. What I want to do is specifically work on the energy calculation. So if this sounds interesting to you, please feel free to stay. If it sounds really boring to you, please feel free to leave. I don't really know. So keep it the main C252. Thanks for coming in. And we're just going to try this. This is going to be like rubber duck debugging hardcore. So I'm going to see if I have Zernal up. I don't. So let's go ahead and describe exactly the problem that we're working on here. And again, if you guys have comments, questions, concerns, anything like that, I realize this is a bit difficult, so please feel free to ask as these questions come up. So I'm going to open up Zernal and bring this over here, that over there. Also, because I did another stream earlier today, like, if I'm tired or anything like that, yeah, I'm kind of streamed out, but we'll see how this goes. So, like I said, we're working on GPUE, GPU-based Gross-Pdevsky equation solver. That is a U. And in particular, we're working on working with the split operator or split step method. So we'll say split op because that's what we've been saying before. GPUE is a superfluid simulation, or it does superfluid simulations. So the idea here is that we have some sort of quantum wave function that basically represents what's known as a Bose-Einstein condensate. This is a situation where you take basically a bunch of bosons, you cool them down to near absolute 0 Kelvin, and when they're at this particular temperature, all of the wave functions kind of condense. So you have one giant macroscopic waves function that describes, 10 to the 5 particles. So this is a large number of particles, all defined by a single wave function. You can calculate basically the dynamics of your superfluid by simulating what's known as a Gross-Pdevsky equation, which is IH bar d psi over dt equals p squared over 2m plus some sort of potential term plus g psi squared psi. Okay, it's something like this. So if we were to take out this term right here, we would be left with basically the regular old Schrodinger equation. But because we have this term in here, we have some sort of coupling or some sort of interaction term that relates kind of every atom in the system to every other atom in the system. So this allows us to have kind of macroscopic dynamics, or rather dynamics between particles in some sort of mean field regime. Point is, we're simulating this particular system with our split operator method. Now, what actually ends up happening here is we have some term over here that's completely in momentum space, some term over here that's completely in real space, and this term over here again will be completely in real space. However, we have one additional thing that we introduced with GPUE to make it kind of a bit more interesting here. So this isn't really just a superfluid simulator, it's a superfluid vortex simulator. So I've said this before on stream, but the idea is if you take a superfluid and you rotate the superfluid really fast, you're going to generate a bunch of small vortices that pierce your Bose-Einstein condensate or your superfluid from the top to bottom. So we get all these very small tornadoes that are kind of in our system. And these tornadoes, they form some sort of triangular lattice. And the idea is that you just have a whole bunch of kind of piercing your condensate from the top to bottom. This rotation term is actually kind of weird to implement in code, right? Because what you do is you subtract out what's known as an omega LZ term. So LZ is an angular momentum operator, which is probably like xpy minus ypx or something like this, vice versa. And the idea is that you have some sort of rotation frequency here, and you're rotating, and by rotating via this operator, you basically apply angular momentum to the system in order to create your superfluid vortex. Now, in order to do this in code, what we do is instead of implementing a minus omega LZ term, we actually create a separate term, which is known as a gauge field, that is then read into this term here. So it's now P minus A, which is a gauge field here, where you'll have AX is going to be equal to Y, and AY is going to be equal to X, something like this. I mean, people didn't know I was going to be streaming, so it's totally fine. And when we do the multiplication out, you'll see that we get the omega LZ term out in the end. In particular, if we multiply this term out entirely, new page before, P minus, we'll do MA squared over 2M. This gives us multiple terms, a P squared over 2M term, which is your typical momentum term. Then you have a squared over M term, A squared over 2 term, which is just a term that's added into the real space potential. But then you have something that's kind of interesting. You get a plus 2 MA term, okay? 2 PA term, sorry about that. We'll call it PA, something like this. But then I think the M's cancel it, so it's just a PA term. So this is entirely in momentum space. This is entirely in real space, so we'll say momentum. This is entirely in real space, but this guy is somewhere in between momentum and real space, so this is in between. And this guy's a pain in the butt to deal with, because in order to deal with this means that we need to take our wave function, which is entirely in, which is complex, you know, it's either, it's got imaginary and real components, and we have to perform basically a one-dimensional Fourier transform along two-dimensional data. So we perform a Fourier transform along X or Fourier transform along Y, such that we can bring our system into a mode that we can then multiply by PAX or PAY, right? So this P term is kind of like a derivative in one direction. And then we have an AX and an AY term, right? And again, if we were doing this with angular momentum, this turns into, should be XPY and YPX. So this means we have something in momentum space and something in real space. So in order to do this computation, we literally just transform forward with one dimension, multiply by the term, transform back that one dimension. So again, this is kind of esoteric. It's kind of hard to follow, and I'm not really sure the best way to describe this. So if you guys have questions, comments, concerns, anything like that, please just feel free to contact me and just say something in chat or something like that. For the most part, I'm not too worried about this right here. This is just something I wanted to mention. What I'm really interested in is something known as an energy calculation. So basically, long story short, what ended up happening is we submitted a paper recently to the archive, and this was recently submitted to a journal, PR Fluids, and they came back with a referee report where they basically said, look, you know, it's a good paper, we're willing to accept it, but we want you to look into a few things. One of the things they wanted us to look into was basically the energy calculation for our system, right? So if we look into the energy calculation here, it's going to be psi h psi. Okay? Now, in this case, psi and psi are your wave functions, and h is a Hamiltonian. The Hamiltonian is this guy over here that we saw before. So this means you basically have 3 different terms that you have to deal with here. A real space term, a momentum space term, and then some term that's in between real and momentum space to deal with your Hamiltonian. So this means you end up getting 3 different energies out of the system. Now, if you were reading the algorithm archive and you've kind of been keeping up to date, we actually have an energy calculation in this book. So it's right here under quantum systems. There's an energy calculation tab. The idea here is rather straightforward, right? Like we have wave function k is equal to FFT of the wave function, so that's going to be our momentum space guy. Wave function conjugate is going to be the conjugate of the wave function. Keep it the main. Is it required to know which space PA is in, or is it in its own separate space? So PA is going to be, yeah, it is required to know what space it's in. And let me just show you that in code. So we're going to cd into projects, GPUE, and git pull origin energy fix, I believe is what it's called. I'm just pulling the latest changes that I made. That should be right. Bah, 1 second. Git branch. Energy underscore fix. Bah, I'm an idiot. Try that again. Okay, so now I'm just going to go into I'm going to go into our evolution function, evolution.cu. So every time step, in order to apply the gauge field, here it is in 2D. What we need to do is we need to do a Fourier transform along one particular dimension. We multiply by that term that is along that dimension. So for example, we do a Fourier transform along x dimension, or I guess along y dimension. We multiply then by ay, which again is probably better done here. It's just a complex multiplication. And then after that, we transform back. Okay, so these are QFFT, exact z to z, plan 1D, and then you have an input wave function and an output wave function, and then you do the inverse. So if you transform along the wrong dimension, like for example, if you were to transform along the y dimension and then multiply by the x operator, it just screws up the entire simulation. Now, one thing to note here, which is actually very interesting and something that I need to look into, for some reason, our QFFT exact z to z function, our plan 1D function here, this should be along the x dimension, but the simulation only works when we multiply along with the ay. Which leads me to believe that there might be something wrong with the way in which we are basically creating these operators. Does that make sense? Like, there might be something wrong in the way that we're initializing these operators so that they're aligned along the wrong dimension. Regardless, the simulation works with this, and I'm kind of not wanting to touch it too much. So I'll look into it in a bit, but right now I really need to get this energy calculation done. So the energy calculation, like I was saying before, is done in a rather straightforward way. We take the energy in momentum space, which is a wave function conjugate. Again, that's what this term over here means, times the IFFT of a multiplication of these guys. So we multiply this guy into momentum space, or we transform this guy into momentum space. Then we multiply by the Hamiltonian, and then we transform back and multiply by the wave function conjugate. Hey Ben, how are you, man? And then we do the same for real space. It's just that because it's a real space term, we don't have to do the FFT. So the big takeaway here is if you're going to multiply an operator, and that operator is in momentum space, you have to transform into momentum space before you're able to operate on that system. So if you have a momentum space operator, you have to do an FFT before you're able to actually multiply by that momentum space operator. I have a huge essay to write and it's already 10 p.m. So I'm going to be pretty half present, but I'm going to try to be mindful of what's going on. Oh yeah, no problem, man. I'm going to see how this stream goes. If it goes okay, I might do another stream like this around the same time because I really need to start doing more GPUE development. If I'm being totally and completely honest, I haven't been able to get as much done as I want to get done, and there's a lot of work to be done before this summer because we have to kind of get the code base ready to go. So I might start doing more of these streams because I tend to find that during stream, even though I tend to talk to people a lot, I still tend to get a lot done. And so I feel like, you know, I'll give it a go. If we end up finishing up the energy calculation this morning and getting it working, I mean, that's a lot of progress because I've been spending literally a week and a half on this energy calculation. Yeah, great way to get me up to GPUE. Yeah, that's true too. That's another reason why I'm doing it. I mean, a lot of people have asked for me to just talk about my research code anyway, so I figure this is a good way to do it. The time zone's not great for people in Europe, but you know, it's okay. We'll see how it goes. Okay, so in the end, this is our energy calculation. We create some energy in K by again performing this operation just for the momentum space components. We get some energy in real space, which is again the same operation, just in real space. And then we have some sort of energy final, and we just sum over all the elements, which is just an integral, and then we multiply by dx in the end. That's it. That's the whole thing. It's not particularly complicated, but for some reason, I'm just screwing up big time with this. And I can't quite figure out why. So what I'm going to do first is I'm going to create a very quick simulation with GPUE, just to show you kind of how it works. And I'm going to try to create a simulation with just a single vortex present in the system. So first thing I'm going to do is actually I'm going to watch my GPU memory. So let's do watch NVIDIA SMI. So I just want to see how much I'm using currently in terms of GPU memory. And it looks like I'm using only 363 megabytes. So I should be able to run we'll just do a small scale 256 cubed simulation, or 256 squared simulation. It's just going to be a 2D simulation with a bunch of little vortices stuck on the inside. So we're going to quit out of here. Well, no, let's leave it up. Why not? Okay, so if I run GPUE-H, it'll give me a help menu where it says, hey, if you want to generate a simple 2D vortex lattice, just run this command here. So I'm going to run this command here. But what I'm going to do is I'm going to modify it so it runs 256 by 256 instead of 512 by 512. And then I'm also going to add 1 here. Okay, so we're going to let this run. Give it just a second. I don't know how long it's going to take. It shouldn't take too long. So 5,000, we're going to do 10 steps of this. So we'll give it a second to run. Holy parameters. I mean, yeah, you're right. We need to fix the way that we're interfacing with GPUE. What you can do is you can actually create a parameters.cfg file, and you can actually just set all these parameters via that CFG file. It was just this particular simulation, we just kind of strung a bunch of parameters together just so people didn't have to deal with that. It was just in the help menu. Okay, so we're going to cd into Pi, which is where we keep all of our Python scripts. And I've got a really dumb Python script in here called plot.py. So we're going to run plot.py input wave function for the data directory, just data. I think that's where I output it to. The grid size is going to be 256 by 256. And then the, I believe that should be it. Oh, I forgot a range. Oops. So now we're going to do range from 0 to, where did this guy end? It ended at 50,000. So it's going to go from 0 to 50,000 in steps of 5,000. Okay. So here we have the initial input wave function. Can you cat plot.py real quick? It's actually available right on GPUE. So if we just go to Pi, it's a real dumb script. I'm not going to lie. It's a really dumb script. It's like 287 lines long. And all it does is it just takes your input argument, whatever the input argument is. It could be your potential, it could be your wave function, it could be whatever it is, and it just plots it. So I've got a bunch of different, like I have plot variable, I have plot variable within a range, I have plot wave function where you have to do some other things to it, plot complex data types, all this kind of stuff. So just depending on what you read in as the item, it will just plot what you want. Okay, so here's the first initial wave function. Here is the second one. You'll note that the only difference between the first and the second one is that this one is slightly bigger. The idea here is that when we read in the initial wave function, it's just some sort of Gaussian. And then we have a harmonic potential, so some sort of large cup that we're holding this wave function in. So what we're doing now is an imaginary time evolution. This is basically finding the ground state of our system. So we're trying to find the lowest energy state. So we've got this trap, right? And then we've got this rotation frequency here. And so what we're trying to do is we're trying to find where these atoms want to sit such that they're as comfortable as they can be with this rotation frequency and with this large trap, right? So first couple time steps in imaginary time, you see them kind of relaxing a bit. And then after that, you'll start to see vortices appear as, again, we're basically dropping in energy. We're continually dropping down our high energy states until we've lost all of the high energy states and we're in the lowest energy. So this is still a high energy state. Again, still a high energy state, still high energy, high energy, high energy, high energy. But here you start to see, as we get closer and closer, we see these vortices in the system. Let me see if I can increase this. So here we have some sort of vortex structure in the system. So what we're seeing here is that we have this Bose-Einstein condensate, we're rotating it, and as we move further in imaginary time, you know, as we propagate forward and we remove all the high energy states, we start to see that these vortex structures start to appear. So these are all little tornadoes that are in our Bose-Einstein condensate, and they're piercing our system from top to bottom. As you keep going, it should be that these kind of create some sort of weird structure. And so they're trying to create kind of like a vortex lattice. So they're trying to create a whole bunch of a kind of a triangular lattice of vortices. But right now they're not doing that because we haven't run it for long enough in imaginary time. But if you kept running it, you would get something like that. I'm going to change the GPUE code that I just ran. And what I want to do is now I want to run it without a very large trap in Z. So before we had kind of this large trap in X and Y, but a very short trap in Z. Now I'm just removing that, and I'm going to change this to 0.4. Why imaginary time? The reason for imaginary time is because of the following. So we're going to do page, new page before. For the split operator method, the idea is that we're trying to find a solution to our quantum system. As you guys know, e to the I theta is going to be equal to cosine of theta plus I sine theta, right? Because we're working with, a quantum wave function, this is kind of a silly way to think about it, but because we're working with a quantum wave function, we kind of want a solution that is somewhat like a wave, right? Because we're going to want to represent it in Fourier components. So our end solution is going to look something like this, right? Now, the thing is, when we actually apply, all of our operators and stuff, it ends up being that we have e to the I h dt, right? So e to the I Hamiltonian dt. And this is going to be our final, this is the final operator that we're working on. And we should have on the other side e to the I psi dt. In order to create the sinusoidal oscillations, we need this cosine and sine term. But in our case, we don't really care about finding the end result. What we care about is finding the lowest energy state. So if we change this dt such that it's kind of tau instead of t, let me try drawing that again, and tau is equal to it, well then this I multiplies with this I and you end up removing the i's entirely. So your solution, instead of being a bunch of sinusoidal waves, is now an exponential decay. And you'll see this exponential decay in the energy such that it's constantly dropping off in energy until eventually you're at the lowest energy state. So every step in imaginary time is essentially bringing you further and further along this here, and then you kind of see that your energy is dropping. This is a dumb way to look at it. It's actually more information available in the split operator method section for the algorithm archive, but that's why we're moving it in imaginary time. It changes your solution such that it's an exponential decay instead of a sinusoidal oscillation. Okay, so this is done now. Let's go ahead and take a look at it. CD into pi, and we're just gonna run the last Python script. There we have it. Okay, come on, keep going. There is nothing in here at all. Crap. I was really hoping. Okay, so then I guess what we can do, I know this rotation frequency should be good, but ultimately what I'm really trying to do, C252 just noticed, let's see. Oh, I'm sorry, I even missed that too, C252. So yeah, he'll be here for a few months over the summer working on GPUE, and that's another good reason why I should do some GPUE streams. And again, guys, look, this is super complicated. If you guys have questions, comments, concerns, anything like that, just let me know, because I need to go through this and explain it in a way that makes sense to you guys. So if I'm saying something dumb or you don't understand anything like that, it's something that we need to look into. Okay, so now I'm going to do ls here, cd backup directory. I don't know why I ls'd there. Let me clear here. And now we're just going to do quick. What am I going to do? I'm going to just run the same code that we had before. Okay, so I'm just going to run it as we had it before so that we have just a large number of vortices in the system. I don't care how many. Okay, and then I'm going to show you exactly what the problem is. In fact, let me show you what the problem is right now. So I'm going to run -e, which will basically output the energy every time step. So here we have the energy. It says energy is 5.3 times 10 to the negative 32. Here energy is 1.3 times 10 to the negative 32, so on and so forth. So basically, we're dropping in energy, but, not by much. The problem is when we have vortices present in the system, the energy just gets really weird and it doesn't do what we expect it to do at all. 1 second. Okay, I'm letting it run. So here we have an energy of 1.4. Okay, so let's take a look at this energy here. So these energies, as they went down, we have an energy of 5.327 times 10 to the negative 33. The next time step has 1.3 times 10 to the negative 32. Now, I don't mind so much that the first time step is off. The main thing is that all of these subsequent time steps should have an energy that is less than the energy before, right? Because we're trying to drop the energy. But for some reason, it's increasing here, and I don't exactly know why. So that's something we need to look into. I just say it, but I really have to get this essay done, and this stream is just way too fascinating to have it be on in the background. Try to come back and catch the end if I write fast enough. Yeah, man, good luck. Don't worry so much about it. I mean, there will be plenty of time to catch you up. So, again, don't worry much about it at all. Again, if anybody has questions on this, just ask. So basically, there is a definite problem with the energy calculation here. Because, again, the energy is increasing here, and it should never increase. So I'm going to run the same simulation real quick, except without turning on the angular momentum step. So this step is the one that basically allows you to do that rotation to create the vortex, right? So I'm going to run it without that, and we're going to run the same energy calculation. And it should be that we find the ground state relatively quickly, and we stick at that ground state. The energy doesn't change at all. This is just a way to show that the energy calculation, the problem with the energy calculation, is most certainly not in the calculation of the real or the potential, or I'm sorry, the calculation of the real or momentum steps. This is definitely a problem with the energy calculation of the angular momentum step, which is something we need to kind of figure out. Again, guys, if you have questions, just let me know. Okay, I'm also going to run this. No, this is fine. So as you can see here, the energies here, 5.327, but then from there, it's all 1.3004, 1.3004. It's always the same after this point. So we very quickly found the ground state, and we stuck with that without any problems. Okay, so we're going to clear here real quick. I'm going to run the same simulation I had before, so we have some sort of system with vortices in it, so I can just play around with it. Okay, let's go ahead and run this. And so now we have some system with just like a whole bunch of random vortices in it. And we're just going to modify the energy calculation for the angular step. And I don't know, guys. I don't exactly know why this is a problem. I'm going to kind of walk through it, see if I can appropriately figure it out. But again, I don't know how far we'll get. This is kind of one of those tests to see what could potentially be the problem. And also, this stream in general is a test to see if streaming this work is actually worthwhile doing, if it helps with the debugging at all. I'm not really sure, so we'll see. So projects GPUE over here. So let's go ahead and open up the energy calculation. So we're going to go into VI source, and then I put it in splitop.cu. So I'm going to go down to splitop here. Actually, energy calc here. Okay, so here's our energy calculation. Now, I just showed it to you in the algorithm archive. I just learned of vimrc. Oh, dude, vimrc is an absolute lifesaver when you're on like some HPC system and they decided to change your Vim configuration so it's all like weirdly colored and everything. You need to update your vimrc file. Otherwise, it just gets really, really annoying. Okay, so let me describe what's going on here. We have this function called energy calc. It returns an energy, which is a double value. We have double star K, double star V, and these basically we're taking from some large parameter class, and we call them a double star value. So we're taking the double star value of K GPU. These are all held in an unordered map, and you might ask why we're using an unordered map. It's just because, well, it's for other reasons. I'm not really going to go into it. Point is, we're using an unordered map for this purpose, and it works okay. It means that we just have to read in one parameter here instead of having to read in multiple parameters. And also when we do abstract syntax tree stuff where people like type down equations that they want to solve, by having everything in a map that's accessed by strings, we can very easily translate from the strings they type in to equations that we end up actually implementing in the code base. Okay, so we have dim3 grid and dim3 threads. If you're familiar with the GPU streams that I did a while back, you'll know what these are immediately. These are basically ways in which we parallelize our system, right? So because we're working on the GPU, we have some sort of large-scale grid that we're performing calculation on, and a certain set of threads within this grid that we're performing computation on in parallel at the same time. We have an xdim, ydim, zdim, then a grid size, which is just d size, a dimnum, which is a dimension number. This is the, we're either running 1, 2, or 3D simulations. So if a dimnum is equal to 2, that means we're running a 2D simulation. If it's equal to 3, we're running a 3D simulation. We have double dx, double dy, double dz, double dg. These are just x, y, z, g, so just basic grid size stuff. We have this Boolean for co-rotating, which basically means we turned on the angular momentum step. We're doing the rotation, so we should see some sort of vortex in the system. And then we have Boolean GPE, which just means we're running with that nonlinear step, the g psi squared term. Okay, now we have the difficult stuff. We have this thing called a cuFFT handle. In order to perform a 1D Fourier transform, basically what you need to do is you need to create a plan that allows for you to do this transformation. So in our case, all these plans are in VI source ds.cu. So when we're creating a plan, we just run this function, which is like generate plan other 2D or generate plan other 3D. And we give it an axis. So if we do 1, 2, 0, 1, or 2, we'll do a Fourier transform along z, along y, along x. And again, we need these one-dimensional Fourier transforms because to implement the gauge field or implement the rotation, we need to be half in momentum space or a third in momentum space in 3D. Okay, so then if we're in, if we're 1D, we're gonna do plan ival 1D, 2D, plan 3D. It's relatively straightforward here. And then all we do is we say, okay, we're gonna do our renormalization factor so that every time you do the Fourier transform, you multiply by the renormalization factor. We have double 2 wave function k, double 2 energy, energy k, energy L. These are all just different energy values that we're going to sum in the end, and then double the final energy. Then we malloc everything on the GPU, so we have an allocation of the conjugate wave function, the momentum wave function, the energy in real space, and the energy in momentum space. We also malloc the energy itself, again on the GPU. We find the vector conjugate of the wave function, and we output this to vector wave function conjugate. Then we perform the GPUE FFT exec z to z, which is just a double-to-double space for a transform. And we say plan wave function k, GPUE FFT forward. So we're implementing the wave function, we're inputting the wave function, and we're outputting wave function k. We do a scalar multiplication of the renormalization factor, and then we multiply wave function k by k, which is your momentum space component that we've defined up here. So momentum space for the Hamiltonian. And then after multiplying by k, we get out energy k, right? And then we free the wave function k because we don't need it anymore. And then we do the same thing over here. So we do GPUE FFT exec z to z. So now we're inversing it. We're going back, and we're just going to do scalar multiplication by the renormalization factor, and then a complex multiplication with the wave function conjugate. So all we did is we moved into momentum space, multiplied by the k operator, moved back, multiplied by the wave function conjugate. I see no reason why this would be any problem. Should be rather straightforward. And when we run our unit tests for GPUE, it seems to be just fine. Because the unit tests, one of the unit tests is to make sure that the energy of a simple harmonic oscillator is correct. And it seems fine. Okay, so let's go over here. Now we have GPE. Double interaction is par.dval interaction. So if we're going to be doing next the real space operator, what we need to do is we need to check to see if we're running with the for a superfluid, or if we're running for just a standard standard Schrodinger simulation. If we're running with a superfluid, then we have to do some additional stuff for the g psi squared term. Otherwise, we can just do a vector multiplication of v and wave function to get energy r, and then we just do wave function c, energy r. So basically, we do the same thing we did before. We multiply in real space, we get our energy r, and then we multiply that by the conjugate. Now let me check something up here because I might have screwed something up. Wave function, real component. So we do a vector sum. I see what we're doing. So what we're doing here is we're initializing a real component, which is going to be what we're going to be applying to our quantum wave function. And the real component is just going to be a sum of the v naught and the g psi squared term. Both of these guys are over here. 1 second. Here. So it's just going to be a combination of the real term here and the v naught here. Yeah, I'm sorry, I got this wrong. So these two terms here, that real component isn't actually in the system. Okay, cool. So then we have the sum here where we sum the two of them together. So we say energy sum, which is going to be equal to energy R and energy K, and it's going to output an energy total. Now the reason I did this is because of the following. So I'm doing an intermittent sum. I'm not summing them all at the end. I'm summing them in the middle. And the reason I'm summing them in the middle of the function here is because if you saw here, we malloced 5 different arrays on the GPU. This is actually kind of a problem. Because if each of these arrays are the size of your grid, and your grid is incredibly large, you probably don't have space to perform this energy calculation at all. You just don't. Because performing this energy calculation, let's say your wave function is 512 cubed. This means, just doing some quick math here, let's just open up Julia. That means that your wave function is going to be, let's see, it's double precision, so that's what? Is that 8 bytes or 16 bytes? Anyway, it doesn't matter. So it's going to be 512 cubed, which is that number. And then we're going to do 512 cubed times the size of your double 2 value, which is going to be a complex parameter. So this is going to be 512 cubed. So this is 134 million elements of double star, or double 2 star. So this basically means that you have barely enough space on a modern, we'll say, Titan X to hold your wave function. There's no way you're going to have enough space to hold all of these other auxiliary variables. So what I'm saying is my implementation of this energy calculation is right now okay, but it only works if you have a very, very small grid size. Otherwise, it doesn't work at all. And so for that reason, I'm constantly freeing, and I'm trying to perform these multiplications in the middle so I can keep freeing more variables as we're going through, because honestly, I just don't want to keep these variables for any longer than I have to. So like down here in CMult, we have energy sum, and then I immediately after that free the variables, just because otherwise we don't have space on the GPU. Okay, so now here's the step that gets really complicated. So we just performed, again, the 2 steps that I showed you before. They're available on the algorithm archive. It's literally just this. So that was all doing this step right here, where we do the Fourier transform forward, we multiply by the Hamiltonian momentum space, and then we Fourier transform back and multiply by the wave function conjugate. And then we did this step for the real component. Same thing, we just did this step. Now, the next bit is the hard part. And this is a bit that I've consistently said is probably incorrect. What we're going to try to do here, or what we tried to do here, is we tried to perform our 1D Fourier transforms along our n-dimensional data, like I said before, with our multiple plans, plan 1D, plan dimension 2, and then we applied our gauge field, same exact way we applied the gauge field in our actual real-time or imaginary time evolution. This did not seem to work. I just tried it for the past week, and it just doesn't seem to work at all. So what I'm going to try to do is implement a new method that basically performs our energy computation without ever having to do a Fourier transform, just because for some reason the Fourier transform stuff doesn't seem to be working, and I don't know why. We have all the appropriate variables, we've stored them on the GPU, I don't exactly know what the problem is. So I'm going to very quickly just create a few kind of operators and stuff that we can use so that we can create very quickly find the derivative of something, and then we can, kind of perform this computation as needed. Because in the end, new page before, all we need to do, here's our Hamiltonian. Our Hamiltonian is going to be p squared minus ma over 2m squared plus v naught plus g psi squared. Okay, let's pretend I can write. Times psi, right? So that's our Hamiltonian. The computation we need to perform is just psi h psi. So it should be no problem. We should have no problem just doing this computation because it's relatively straightforward. Sure, p is going to be a d by dx term, but I mean, we can just perform a derivative relatively quickly. So I don't see a problem with that. So we're going to try it. We're going to see what happens. I'm just going to create a derivative function, and we're going to go from there. Again, guys, I assume that people have questions, comments, concerns. I mean, there are a relatively high number of people watching from what I expected, but like no one's in chat. So I've got a feeling I've lost everyone. I mean, so just feel free to just ask questions or talk about whatever you want to talk about. That's totally fine. So now let's go ahead and open up a new file where we're going to perform, where we're going to create our derivative, I guess, kernel. So it's going to be VI, where should I put it? I guess it's going to be source, and I'll put it into, not unit test, dynamic evolution example, init kernels, probably kernels.cu makes the most sense. Okay, so here's just where we have a whole bunch of kernels. It's only 683 lines long. So I'm going to create first a global kernel here. So it's going to be global, and we're just going to call it derive. And I want to set this up in a very particular way that I wrote down here. So it's going to be global void. Oh, I forgot a void. Derive. And then we're just going to go in here. We're going to say data, output, stride, n, and dx. That's what we need. So we're going to want to do, this is going to have to be a double 2-star, I believe. Is that going to be a problem? A double 2-star? In fact, no, it should just be a double star. So it should be a double star data. And then we're going to have to do int stride. Then the next thing we need to do is, the output data. I forgot the output data. Double star data, int stride, and then we're going to want to do, I think, a double dx and one more variable. Int n. So int g size, and then double, what's going to be? It's going to be dx, I believe. So double dx. Okay, opening this up in there. Now we're going to have to do what we always do, which is just kind of define the global GID, the global index that we're working with. So that's going to be int GID is going to be equal to get GID 3D3D. Don't ask why it's named this. Honestly, the person who was working on the codebase before me just named this that. I don't exactly know why. I'm turning in, haven't been watching your work on this project, so I'm just so soaked into it. Oh, cool. I'm glad you like it. Again, if you have questions, comments, concerns, just ask. I'm gonna totally try and answer it as soon as I can. And the reason I'm streaming this, this is actually my daily work. The reason I'm streaming this is because I find that I'm genuinely just slightly more efficient on stream than I am working. And if anyone's known my stream, you'll know that I'm not that efficient streaming, but it is what it is. Okay, so now let's go ahead and perform this guy. I think I can just directly take this that we have here. So we're going to say if GID plus stride is less than G size, then we're going to say out of GID is going to be data of GID plus stride minus data of GID over dx. That should be correct. And same thing here. So what we're going to do here is we're going to try to perform a 1D Fourier transform, right? Along, or 1D either this way, or this way, depending on which dimension you're in. And we're going to try to do this such that you can perform the 1D Fourier transform along, your n-dimensional data. Except in this case, rather than doing the Fourier transform for a derivative, we're actually just going to be performing the derivative flat out. Does that make sense? So before we were using a Fourier transform for the derivative, now we're just doing the derivative. So the idea here is that if you want to perform a derivative along x, then your stride is going to be 1. If you want to perform a derivative along, let's say y, then your stride is going to be x dimension. And if you want to perform a derivative along z, then your stride is going to be x dimension plus y dimension. So this, so let's say global kernel to perform derivative. Come on. And in here we're going to say for x dimension, let's say Fourier transform. I'm sorry, derivative stride equals 1. I'm just going to say yank pp, and then for y dimension, and then for z dimension, and we're going to say stride is going to be equal to x dimension, and then down here should be x dimension times y dimension. Something like this should work. We're a bunch of rubber duckies. Yeah, I mean, we'll see how this goes. I mean, the question is this stream going to be successful or not? Just depends on whether we can get anywhere with this or not. Okay, so now we have this global function derive. I'm going to have to put this into the include file real quick. So let's go ahead and quit out here. Let's go into VI source, and it should be, include, and it's going to be kernels over here. Okay, and now we're just going to go ahead and add this in. I guess I put it at the top, so I'll just put it here. It's not too big of a deal. We'll just grab it here and there. And let me just go ahead very quickly do this. Oh, hello there. Let's do this. It's going to be brief subtraction, so I'm just going to say derivative of data. Derivative of data. And in group GPU should be fine. I should add in some parameters here. So we're going to say param. And here we're just going to say, oh, did I use tabs or spaces before? I think I used spaces. I'm really good at being a rubber ducky. Ha, well, thanks. So here, parameter is going to be, it's just going to be input data. And then the next one's going to be output data. Then after that, we have a couple more parameters. Yank p, this is going to be stride of derivative. And I guess I don't really know how to notate this. So I guess I'm going to say, ooh, hello there. Let's try this one more time. For xdim derivative use stride 1. Let's try this. Xdim, oh, it's going to be pain, isn't it? Ydim, zdim, derivative use stride 1. Xdim, xdim times ydim. Okay, I'm just going to format this a bit. And again, guys, just keep talking if you have questions or anything like that, or if you see something that I'm doing wrong here. So the next we're just going to do, finally, another param, which is going to be the G size at param. And it's going to be the grid size for simulation. And the last one's going to be the double dx. I guess I shouldn't have called it dx. I probably should have called it dg or something like that, but it doesn't really matter too much. So I'm going to say param, and this is going to be a dx value for derivative. Okay, so this should compile, no problem. I'll check. It doesn't compile because I'm an idiot. What do we have here? Kernels.h31 duplicate parameter name? Duplicate parameter name? global derive. Do I already have a derive in here? Parameter name dx. Data. Oh, shoot. I should have done input. These are data and out, not data. And here I'm gonna have to do the same thing. Okay, give that a second to make. And then we have the derivative kernel kind of ready to go. And we'll go ahead and try that with the angular momentum step and see what happens. Get GID 3D. What did I misspell here? Get GID 3D. What? Oh, is this because I have it defined? Yeah, maybe I should define it further down. Okay, let's define this underneath that. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we'll do D15D, and we'll just define it just right after that. I don't really care so much. I need to do a better job at like putting all these functions in the appropriate place, but I just right now I'm just trying to get something done. I'm not so worried about making it look very beautiful at this point. We just got to get something working, and then once it's working, we'll refactor. Okay, does this seem to be working okay? I mean, it's making. Good, okay, so it is now built. Okay, so let me run, again, the same computation I did just a second ago on GPUE. Let's see what we got. Yeah, so this is the problem, right? So I just performed the computation I did a second ago, but for some reason now our energies are negative. I don't know, we're just running into problems here. So we need to fix this energy problem. We shouldn't be getting some crazy negative energy. That doesn't make any sense, not for this simulation. So let me go ahead and get some water. Again, though, if you have questions, anything like that, just ask. Okay. Also, I'm going to clear the chat real quick. This is just because there was potentially some personal information on the chat that I probably should have cleared a while ago. I realize, you know, obviously if you guys offer up the information, it's fine, but I don't know. So I'm going to go ahead and work on the energy calculation now. So we're going to go into vi source split op.cu, and ultimately what I'm trying to do is make the energy positive. I just want a standard positive energy value when I'm using the angular momentum step. So I'm just going to gut the current angular momentum step because I think the other steps are probably fine. It's just not the angular momentum one. And we'll see what happens. You know, I don't know how this is going to go. So let's think about this and get this working. So here's the co-rotating and dim number greater than 1. I'm just going to gut this whole thing. So again, this has to be done for 2D and 3D simulations. And we're reading in AX, AY. Oh, I probably should have kept some of that. Let me try this again. Okay, so we're down at the energy calc. Let's move down here. And let's see what we got. So we have double renormalization factor X and Y. So I know for a fact we're not going to need these because we're no longer going to be performing Fourier transform. So we don't need that. Double time, we don't need this. Planned 1D, don't need that. CUDA-malloc energy L, we're going to need this. Double 2 AX and AY, we're going to need that too. QFT double complex. We shouldn't need to have to do this, I think. I don't think we have to make them complex. I think we're okay leaving them as doubles. Now this is something interesting. If we're performing a derivative on our wave function, is there something special I need to know for a derivative of a complex value? Or do we just perform the derivative or do we just perform the derivative separately on the real and complex components? That's something I need to look into. So let's see, we have dim num equals 2. Again, we don't need these guys. We're doing it a different way now. Okay, we have QFT handle. We don't need these. CUDA-malloc AZ, we do need this. We don't need that. And let's go ahead and get rid of all this. And then CUDA free AZ, that's the correct place to put it. AXAY should be fine. CMult, these guys we need to keep. Okay, so now what we need to do is add in the derivative bit that we just added in over there with the other function. Now, one thing I want to be clear about is that that derivative function that we added in works on a double star value, but we're going to have to perform the derivative on actually a double 2 star. So let's actually create a new function for performing a derivative on a double 2. In fact, maybe it would be best to create a template here. that would allow us to flip between double 2 stars and double stars, because I think ultimately there isn't a difference in the code. I think the code is the same. But let me take a look real quick. So we're going to go VI source and kernels.cu, and let's go to derive. Okay, so we have derive down here. Okay, no, there will be a difference because we have to do this over dx term. So we're gonna have to modify it anyway. So I don't think we could do a template here. Not easily. We'd have to do a whole bunch of different stuff. So we'll do double 2 in, double 2 out, and then we'll see out did.x. And then we're just gonna add some .x's to all of these guys. So grid.x, .x here. We're gonna yank and paste it here. We're gonna do y, and y over here, and y over here. And now you might be confused as to why we're using this notation. So the x and y for the QFFTWs, QFT double, sorry about that, corresponds to the real and imaginary component respectively. So by doing it this way, we can just do a derivative along real space and complex space without any problems. I think we're allowed to do it this way, but I'm not entirely sure. So let's go into VI include, and then we're going to include kernel.h, and let's just go down to derive, which is right there. And we're just going to copy this guy and paste it again. I mean, yeah, I realize we should probably do, no, we don't need to change dx. That was what I was saying. So dx here stands for the spatial parameter, right? Whereas the .x and the .y stand for the imaginary real component of the input complex double 2 value that you're reading in. So because of that, dx is still fine. I understand that nomenclature-wise, it could probably have a better name, but it's ultimately fine. So let's do double 2 here, and another double 2 there. Right and quit. Let's go ahead and make this guy. Should make without any problems. Okay, and I'm just going to run the energy calculation one more time. So just the same simulation we did just a second ago, and just check the energies. These should be positive. Just popping in for a moment, almost done the essay. What is the comment documentation format called? What we're using right now is... Oh shoot, what is it called? Let's see. I don't remember what it's called. Introduction to GPUE. We should have purpose of GPUE. Oh no, it's going to be under development, I believe. And then we have the Doxygen. That's what it's called, Doxygen. Yeah, so this is going to be Doxygen. So we have the documentation here. So you have like all the namespaces and stuff. We just have this defined in such a way. Yeah. I have a lot of work to do on the documentation, no doubt, but that's okay. We're getting there. Okay, so this seems okay. For some reason, the energy is still negative. I don't understand why the energy is negative in this case, but we'll just keep working on the kernels here. So we'll work on split up, and we'll go down to energy, energy calc, and then we're gonna look down for co-rotating. Okay, so here one more time. So here's the co-rotating stuff. So this is if we have the angular momentum step in addition to the other computation. And we're just going to perform our derivative along the QFFT double complex, which is the wave function. So I think we're going to have to malloc another object here. So we're going to do double 2 star. And this double 2 star is going to be of, I guess it's going to be, we're going to call it DWFC. All right. Which stands for the derived wave function. I know that's dumb. There's probably a better, what I don't know what else to call it right now. So we're just going to say double 2 star here. And why not? Let's just go ahead and put all these on the same line. So let's do double 2 star, star AX and star AY. Just so they're all just defined on the same line. Doesn't really matter too much. Let's see. Looks eerily familiar to JS doc format. It only makes sense that JavaScript wasn't the first to do it in that way. Yeah, I'm not really sure. I know Doxygen is very commonly used, especially for scientific computing, but I don't actually know if it's used like more or less in different areas. I figure the format's probably pretty common. Okay, so we did W2 star. Let me actually put the star over here, there. Okay, we're gonna CUDA malloc this energy L. What on earth am I doing? Energy L, which is the angular momentum energy. Get this guy go here. You know, I was thinking about this the other day. Calling it the angular momentum energy doesn't really make very much sense because we have auxiliary gauge fields that we could very easily read into, but regardless, this is the nomenclature we're doing for now. So we did a CUDA malloc here. We're going to do another CUDA malloc, yank, and paste up here. And this is going to be for the wave function, so DWFC. C. And size of W2 times G size. That should be okay. So we're going to copy the wave function onto energy L. Now my question is, I think actually we don't need this DWFC. I think we can actually just use energy L. So DD there, and instead of copy, we're going to use the derive function here. Okay, that we just add in. So the input's going to be wave function. Then we have energy L. What else do we have here? How is CUDA malloc different than normal malloc? Using GPU memory instead? Yeah, that's basically it. There's some small scale differences in terms of like how you read in the values, but it's mostly the same. Looks like JavaScript doc is a derivative of Java doc and PHP documentation formats, each of which are inspired by or at least related to the same documentation format. Huh. Interesting. Okay, so now I'm going to go ahead and just open up the, let's just open up the file I was just in. Derivative here, so we're going to want data out stride. So this is going to be an X dimension. This is going to be an X dimension. Ah, no, we're definitely going to have to do this. Shoot. Let's go ahead and do the copy again. So we're going to have to perform a derivative, but I don't know how to perform like an antiderivative. Does that make sense? Like, yeah, I know it's an integral, but like, let's just do wave function energy L, and let's just have our DWFC like we had before. Start DWFC. Okay, so now we have the DWFC. What I'm looking to do is, I guess since we have the AX and AY in here, I guess we're just going to do this here. So we're going to say if divnum equals 2. In fact, I don't even know if we need this if divnum equals 2. Let's just see, because we're going to have to perform these steps anyway. So we're going to say derive grid threads, and then we're going to have to read in the wave function and then the derived wave function. And then we have to read in the other variables here, which will be stride, G size, which is, I think, already defined. And then we're going to have to read in double DX, which should be this guy here. Now we're going to have to perform a similar guy later, which is going to be for the Y dimension. So it's going to be this, and instead of doing 1, this will be X dimension. Okay, so now we did the derivative. Now what we're going to have to do next is multiply this derivative, or this derived wave function, by the, I guess, complex AX. So we did need to make these guys complex. Let's see, CUDA always confuses me. Never know when it is like C and when it's like C++. To be fair, this could be a notational problem with how I'm writing C++ code. I tend to write it somewhere in between C and C++. For the most part, CUDA is C. I sometimes add in some C++ features, but for the most part, it acts and works like C. So if you know how to code in C, you're fine with CUDA. Okay, so we're going to derive here. And then we have the derivative of the wave function. To be honest, I really need a coding partner to keep me busy. I have all this time, but spend it reading more than coding. A few years back, me and a friend of mine were working on a project together and we got so much done amidst those days. Yeah, I totally understand. Honestly, it's kind of the best way to, I think, get better at programming is to program with other people. So yeah, I mean, that's part of the reason why I'm doing this stream right now, because honestly, in the mornings, I tend to not get so much work done. Like, I get a lot done in the afternoon. It's just like, I do my morning stream from 5 to 7 o'clock a.m. Then I work out in the morning, and then after working out, I go into work. But just honestly, in the morning, I just don't get anything done. See you, Su252. Thanks for coming in. So I needed something to kind of kick me in the butt and get me working on this kind of stuff. So we perform the derive here, and we output the derived wave function. And then after we have the derived wave function, we just perform a CMULT, which is a complex multiplication with grid, threads, and it should just be input-output, so we should just do, oh, okay. This is actually kind of interesting. Okay, well, we'll see what we need to do here. But we're going to perform a CMULT of our wave function, and our, it's actually going to be our derived wave function. How do we derive back? I see, so this is just an operator, right? Okay, so maybe I'm doing this wrong. Maybe what I need to do, maybe we keep this as energy L. I'm gonna see what happens. So we're gonna keep this as energy L. We're gonna perform this derive function here. So we're gonna DD up here, paste it here. So energy L is gonna be a temp variable for now. We perform the derivative here. Yeah, okay, so we'll do energy L. Okay, and then we do the energy L, we have the derived wave function, then we perform a CMULT, dd paste up here. And let's just go ahead and do d3d, so we have everything defined. I'm sorry. And then we're gonna have to get out our AX and AY, which are just going to be size of double. Yeah, so it should just be AX is gonna be equal to par.dsval of AX GPU. We want the GPU pointer here. Then we're gonna do the same for AY. And par.ds value AY. And now we have to make them complex because I'm an idiot. So now we're gonna pop down here and we're gonna use the make complex function. I'm gonna be honest, I'm just gonna grab what we had before. I shouldn't have written over it. So let me just go to GPUE over here and let's do branch energy fix or whatever it is. We're gonna go to source and then we should be able to go to split op in source. And now we look for energy calc. Okay, pop down here. So it should just be scalar mult. Let's see, energy sum, co-rotating. So it's gonna be Kutamalik copy. Yep, Kutamalik. And then we're gonna do, I see, I just did this directly. Yeah, that's what I should do. That makes more sense. Oh, I'm sorry. Okay, so we don't actually need to grab these guys because they're always double twos. Fair enough. Okay. So now what we're gonna do is we're gonna take the ds value that is AX, and now we're gonna multiply it. So it should just be CMULT, dd here, CMULT d wave function with, actually it's just gonna be energy L. It should be with AX, and then we're gonna output energy L. Okay, so we have this done. So now the next thing we're gonna do is derive the wave function, or the energy L output, here. So it's gonna be energy L, and then it's gonna be output energy L. Yep, X dimension, except in this case, it's gonna be, yep, that's correct. So now we're gonna multiply it by the AY. Okay. Okay, so that's fine. So now we're gonna multiply by the AY. We don't need this anymore. And then the next bit we're gonna do is double 2 malloc AZ, CUDA malloc here. And I'm just going to do the same thing I did before with the make QFFT double complex. Just going to put it down here. Oh, that's so close. Okay, so we're going to do Z, and we're going to do AZ GPU. So now we have that. We're just going to derive along Z. So let's go ahead and do yank to yank here, and paste it down here. Let's paste it here. Open there. Okay, so now we're going to do the derivative, except this time along the Z dimension. So it's going to have to be the stride of X dimension times Y dimension. And again, dz isn't correct here, so this should be dy. This should be dz. Nope. Come on. Okay, and then we do a CMULT with AZ. Okay, so in this way we performed a derivative along one dimension, multiplied, performed the derivative along another dimension, multiplied, performed the derivative along the last dimension, and multiplied. All this left is a CMULT with energy L, and then we should be able to do the energy L sum. We'll see what happens. So I'm going to go ahead and make this, and we're going to see what happens. Okay, it's made. So let's run our GPUE code. Energy's positive. That's nice. Still positive. Still positive. And we're in the right order of magnitude, so we're getting there. We should have a vortex present in the system. I don't like the fact that it's increasing in energy here. Yeah, I don't like that at all. But I mean, we have vortices present in the system, so maybe that's fine. Okay, fine. We're in the right order of magnitude for the energy of the output system. That should be okay. I'm going to cd into Python just to make sure the energy computation here didn't do anything dumb. So I'm going to do the last Python here. So here we have this. We should see vortices appear in the system as we're going through. Yep, okay, here's our vortices. So there's nothing wrong with dynamics here. Now I have one last thing to check. So we just performed the derivative as we expected for dx, dy, and dz. What I want to do is I want to modify the energy computation code so it doesn't use Fourier transforms for the rest of the energy computation. And the reason I want to do this is so that if we if this derivative function is working and we get the appropriate energy out without using Fourier transforms. First of all, we don't have to malloc as much data, which is nice. And the second is that this is kind of a way to guarantee that the energy computation is working. So what I'm going to do right now is I'm going to go ahead and commit what we have, so I can always come back to this stage. Git status, git add, include star and source star, git commit -m, adding, I guess we'll say derivative function and implementing it. Oh my gosh, for energy calculation. Okay. Now we're gonna do git push, origin master energy fix. Okay, so in principle, what we have should work. In practice, it's gonna be hard to check unless we perform some sort of similar derivative for the d by dx term in the momentum component, right? So this momentum component here, new page 4, is actually a del operator. So it's d by dx squared. So it's going to be like, right, because we have a p squared over 2m. This turns into a d by dx squared, right? And in fact, this is actually going to be a del operator, which is d by dx plus squared plus d by dy squared, right? So what we're going to have to do is actually perform this operation on our wave function. Since we have the derived function, we can pretty easily create a del operator, and that's what I'm going to try to do now. So to create not only the derived function, but also the del operator, because we're going to have to need, I guess, yeah, we're going to need a number of different components here. See you, Ben. Thanks for coming in. Okay. Yeah, I guess I lost everyone with this code because like there aren't so many people watching, but that's okay. You know, we'll see. 1 second. Yeah, I'm sorry. I'm checking the stream notifications over here. Okay, but regardless, we have something that should be working now. So I'm going to very quickly create this del operator. So let's go into vi source and kernels.cu. We have derive. Let me just look at up the Laplacian real quick just to make sure I'm not being dumb. Laplacian operator, del squared, is just del.del, which should just be, yeah, the sum of all the d by dx's. Yep, just making sure I'm not being dumb. So here, I guess we'll just create a new function that's called the Laplacian. And to do this, I guess what I'm going to want to do is I'm going to want to create another set of derived kernels, but these are meant specifically for device output. So we're going to do, basically grab these guys exactly as they are before, but this time they're going to be devices. Okay, and we're going to do the same thing up here. I know there's probably a better way to do this with templates and stuff like that, but I'm not so worried about it right now. I kind of just, again, want something working, and then we'll refactor in a bit. Okay, so we have derive here. So we don't need output anymore because we're going to be doing this such that it returns the output. And so we're going to do double dx up here. Nice. D. We're going to do the same thing up here. So double out star, we're going to remove that. And go over here. There we go. Okay. Now all we have to do is basically output the correct data here. So I guess what we're going to say is we read in data. So do we have to allocate the data here? You know what? Maybe I'll just do a global. Let's just do a global. I think it's easier. It's not worth it. Okay, so we're going to very quickly create a Laplacian function. It's going to be the same as before. So global void Laplacian. And here we're going to do double 2 star data. And I guess we're going to do the same thing we did before. So double 2 star output. Then we're going to have to do, I don't think we need a stride in this case, because the Laplacian is going to be along all dimensions. But what we probably need, let me think. So it's going to have to be along the x dimension and the y dimension. So we certainly need an int g size. And I guess we need a dimension number. So we're going to say, oh, and also I guess a dx. So we're going to need a double dx, double dy, and double dz. Maybe we just read in all of them for now. So we're going to want to do xdim, ydim, int ydim, and of course int zdim, which I'll just put down here. Then after this, we're going to do double dx, double dy, double dz. It's annoying and messy, but it'll do the job. Let's go here and there. And I'm just going to yank 3 yank and paste it down here too, because we're going to want to do the same thing for 2D, and we're going to need just y and x dimension. So I can remove that guy, and I can remove this guy. Okay, and this will just allow us to differentiate between the 3 and 2D one without any problems. Okay. Int gid 3 int gid is equal to get gid 3d here. Okay, let's go ahead and yank this and paste it down here. Okay, so this is the thing that allows us to get our grid ID that we're on. And now we're just going to say, basically we have to perform a derivative for each of these guys according to, you know, actually maybe it's best to make this as just a host function. Like maybe we don't even need to put this on the GPU, because we're just passing around GPU memory anyway. What exactly you're trying to simulate? We're just doing basic vortex dynamic simulations. So, oh, sorry about that. So we have, you know, a superfluid system. You rotate it, you get a bunch of vortices. Right now we're just checking the energy computation for it. Again, this is, I covered it a second ago, but it's not that big of a deal. The idea is just, again, you get a whole bunch of these tornadoes in your system as you rotate it, and we're just simulating the dynamics as they move around with time. So just for the record, cd pi, I'll just show you for an example what we're looking at here. I'll do it over here. cd pi, let's run Python. So we have this superfluid here. So this is just our superfluid. And basically the idea is we have all of these basically small tornadoes that are just piercing our system from top to bottom. And you can just see them, you know, all in our system here. And then the idea is just, you know, we run them and we see the dynamics, and that's kind of what we do. So we'll see how it goes. Right now I'm checking the energy computation just to make sure what we're doing is accurate. And then once that's done, I mean, that's a project I wanted to get done this morning. So I'm actually relatively happy. I realize this stream has like basically no viewers, but I don't really care so much about viewers because honestly, the whole rubber duck debugging thing is actually helping out a good bit. So we're actually getting a good amount done, even if we don't, you know, have too many people watching. And so that's kind of okay. I might consider doing more of these streams later. I'm not really sure. We'll see. So we're going to cd into backup directory, and we're going to open up the file we just had. Source kernels .cu. So we have these Laplacians. I'm almost convinced that these guys just need to be host functions. In fact, I'm almost entirely convinced these can just be host functions. I don't think we need them to be global functions. Yeah, I'm entirely convinced they can be host functions. But how would I want to do that as a... Nah, it's better to make them host functions. Okay, so what we're going to do is we're actually going to put these in a different file, I think. So let me see what files we have. I want to put them in the operators file. The source and operators. And here we have double sign. I'm just going to create a new one, which is void Laplacian. Okay. We're just going to grab the same guys we did before. So double, I guess it's always going to be double 2 in our case. Double 2 star data. Double 2 out. Then it's going to be int x dimension, int y dimension, oh, come on, int z dimension. I feel like I missed something. Oh, I almost certainly did. Let's see what we have here. Drive. Data out stride. No, I think this is okay. Huh. Oh, it was a global at the start, obviously, because we're not doing it as a kernel anymore. So we're gonna pop here in Z dimension, pop down here, and we're gonna say double dx, double dy, double dz. Okay. Now, of course, we have to create our 2D version of this too. Hello, what are you doing, dog? Oh, I see your problem. Nice. So now we're going to create our 2D version, which is just going to be this guy. So it's going to be yank 4 yank, yank 5 yank. And we're going to change this to be the 2D variant. So we're just going to remove the Z dimension here. Yeah, there's like no one watching, but that's okay. I understand. It's kind of a weird thing to do. Okay, so we have the derived kernels. We're reading in kernels.h, so we should just be able to, I guess we're also gonna have to read in grid and threads. Int, let's say dim3 and dim3 threads. Same thing down here. Oh, okay. So now we have the grid and threads. It's kind of a clunky way to do it. I think I almost would have preferred to do it. Yeah, let's do it. Bah. Let's just read in the parameter class. So dt here, and we're gonna do the same thing here. And we're just gonna do grid ampersand par. Is it capital G? Yeah, ampersand par. Oh man, so then we're gonna have to do int z dimension here. Okay, and then we're gonna do the same thing down here. So it's just gonna be grid ampersand par. Okay, so now we have this guy done, ready to go. And let's go ahead and get this done. So we have the derivative. So now since we have the derived function, we're just gonna have to perform the derived function twice along each respective dimension. So since we have the x dimension, y dimension, and z dimension, we should just be able to perform the appropriate computation as necessary. So we're just gonna say, since we have the output data, I guess we're just gonna say, out, so it's just gonna be derive, grid and thread, so it's gonna be par.grids. Let's just get defined in here. It's gonna be equal to par.grid, and then we're gonna have a threads equals par.threads, and then down here we're just gonna do grid and threads. Okay, and then we just read in the appropriate functions. So let's go ahead and go into the energy calculation since we have it up. VI source and split up. Okay, let's go down to energy calc. Okay, so we have this guy here. Let's see, where did we have it? Derive there. So we have derive here, it's just gonna be grid threads, and then we just read in what we want to read in. So it's gonna be data, and then it should be output data. Then we just have to read in what we need for the stride and stuff. So the first one's going to be along the x dimension. So the stride should be 1. And then we should have g size, which is just going to be x dimension times y dimension times z dimension. So we'll just do g size. It's going to be equal to x dim times y dim times z dim. There we go there. And so we're going to have g size, which I did lowercase g size. And the last one's going to be dx. Okay. And now we're going to do the same thing, yank paste, except this time it's just going to be the output data. We're just dealing with the output data. Okay, so in the end, we're going to have to sum everything together, which is going to be a bit of a pain, but it shouldn't be too big of a deal. So here we have the derivative along x. Yeah, so we have the derivative along x. And then we're going to have to add in the derivative along y and the derivative along z, I believe. So I guess what we actually need to do is create 3 temporary... No, we don't want to do 3. We just want to do 2. So let's go up here and let's go ahead and define a temporary variable here. So we're going to say double to star temp derivative ativ. Why not? And we're just going to go ahead and malloc this. So we're going to say CUDA malloc void star star. And it should be temp derivative. Do I need an ampersand here? I always forget. Yeah, I do. Ampersand temp derivative. Okay, and then after we do the temp derivative, we're gonna do so we have the void star star there. So then we do the temp derivative, and then it's just gonna be size of double 2 times g size. Okay, So now we have it defined on the GPU, and here we're just going to do temp derivative and temp derivative. There and here. Okay. So now what we're going to do is we're going to set the output. Out is just going to be a copy. So we're going to do copy of grid threads. And we're just going to copy. Do we have the copy over here? No, we don't. So we're just going to copy the temp derivative to the output data. So it's going to be out. Now we're going to perform the same routine for the Y dimension here. So we're going to do yank 3 yank, paste it down here. And now for the Y dimension, we're just going to change the grid size here to be X dimension. And down here it's going to be another X dimension. And we're going to change this to dy. Okay, so now we have the two derivatives. This should be fine. It's just in here I screwed something up, so we want this to be temp derivative. There. And we're going to want to do the same thing here. Go paste that there. Okay, so now we have the two temp derivatives. Why am I a semicolon over? Temp derivative, temp derivative. Ah, it's because of the X dimension. Yeah, fine. Okay. I'm just going to go ahead and put this down to the next line then. Okay, good. So now we have that. So the next thing we need to do is sum them together. I don't remember if I have a sum function or not, so I might need to create that. Let's go to VI source, and I guess it's going to be in kernels. Let's look for sum. Energy sum. I just do in 1 and in 2. So I guess I'll just do that one. So it's going to be energy sum. Ah, shoot. Screw you. Let's try that again. In here, sum. Okay, I called it energy sum, but it should be fine. And this is going to be equal to grid threads. And all we're going to do is we're just going to sum these guys together. It should just be double in 1, in 2, and then out. So it's going to be temp derivative. The output, and then out. Okay, now do the same thing for the Z dimension here. Okay, the only difference here is that we change this derive so it's now along X dimension times Y dimension. There, and we do the same thing over here. And then we change it to DZ. RZ. Z. And then a Z along here. Okay, so now we have the energy sum here, and it's going to be temp derivative out, out. And that should be it for the Laplacian for 3D. And let's go ahead and make the 2D one, which is just like the 3D one, just with less steps. So we just grab this guy here, and then we just don't have to do the Z dimension stuff. Okay, there and there. And let me just add some spaces here, just because I feel like it. Okay, so we have that sum. One thing I need to do is free. So let's do CUDA. And we'll just free the malloc temp derivative. Here, there. Okay, yank and paste this down here. And that should be it for the energy, or for the Laplacian. Okay. So in principle, I should be able to modify the energy calculation now so that we just perform the Laplacian. Is it Laplacian or is it the del squared? No, Laplacian. Yeah, this is correct. Yeah. D by dx, then you sum them all together. Yep. Okay. So let's just double check this real quick. Grid threads. Let me go ahead and make this to make sure it makes. And because there could be an error somewhere in here. Aha, there is. So let's go to line 7. Laplacian, what's your problem? Error expected a comma or a parentheses. So let's see. Error expected a parentheses. Identifier x is undefined. Let's see. What is your problem? Void Laplacian. Void Laplacian. Let's go to 8. Return value type does not match the function type. What? 9? What do you mean? Oh, I'm in the wrong file. Of course I'm in the wrong file. No, I'm in the right file. This is operators. Make. Kind of odd question. I'm finishing up my bachelor's in pure mathematics this semester with a minor in computer science. Whenever I'm working on some pure exam or a computer science program, I find I enjoy the process of work. Yet whenever I'm on my own time, I never seem to drift to actually work on extra math problems or personal programs. I don't seem to have a drive to do that work for myself, only when it's for some imposed project. Yeah, I'm clearly missing a closed parentheses before line 7, but I don't understand where, because there's clearly a parentheses here. Let me get to that question real quick. Can you empathize? In some ways I can. This doesn't match anything you've ever dealt with, but in some ways I don't. So for me in particular, I find that, I've just been working in the algorithm archive for so long. Usually when I have free time, I don't mind having a bit of downtime, because honestly, I get up in the morning at 4:30 in the morning, and then I do streams from 5 to 7, and then I work from 9 to 5, and then I come home, and honestly having an hour of downtime in there is not so big of a deal. But in terms of like finding stuff to work on outside of work, I do understand this, because it kind of feels like, if you're working and you're working and you're working and you're on some esoteric, pure mathematics thing, it's rather difficult to use this pure mathematics anywhere else. And really, in order to get into it, you've got to just read some papers or something like that, which isn't naturally the most interesting thing to do. You know what I'm saying? But I don't know, you just kind of get into it like you get into anything else. Like, I don't personally like the idea of playing video games, but that doesn't mean I don't like playing video games. I don't like the idea of going to work out, but I enjoy working out. You just got to do it, and you're kind of conditioned to do one thing. So then you just condition yourself to do something else, And sometimes you need to push. Sometimes you need to install an application that makes it so you don't watch YouTube anymore. Or sometimes you need to do something that forces you to think about the actions that you're doing at any given point in time, But for the most part, I think finding the motivation is kind of a problem that you need to figure out. Like, it's a problem that every person will figure out for themselves. I empathize with a username. I try to find others who have interesting questions. My skills to solve the problem. Physics, mathematics degree. Yeah, I mean, for the most part, for me, I find that the programming problems are the most challenging and interesting. Or not challenging, but they're the most interesting to me, because there's something that I can immediately help with and I can kind of play around with. It's just fun and interesting. Meanwhile, for a lot of other problems that I could use my expertise for, particularly in the area of physics, I don't find as interesting, because it's kind of difficult to find some weird physical system that I could simulate and work on, It's just a different thing. Let's see. Yeah, I keep defaulting to low effort habits like browsing YouTube whenever I have free time, instead of some kind of self-betterment or working on something fulfilling. I mean, I'm going to be honest, there's nothing wrong with browsing YouTube either. Like, if it's something you enjoy, if it's something you like, I mean, do it. Don't feel bad for taking your own time and just chilling for a second. On the other hand, if you feel like you're wasting your time, I also understand how that can lead to a lot of unnecessary stress. So, I don't know, I guess the best solution here is just to dive into things that you find interesting. Maybe read some archive papers every now and again. Try to find a project that you enjoy working on. This type of stuff. For me, I found that I can just endlessly read papers about algorithms. So I always read more stuff about algorithms because it's incredibly interesting to me. And there's always more code to write, there's always open source code available that you can mess around with. So this is kind of where I tend to find my enjoyment, what I tend to do in my free time. I just read papers. But this doesn't mean that that's necessarily what you enjoy doing. Maybe you enjoy contributing to open source code or something like that. I don't know. It's just a matter of finding what it is that you like and figuring out how to replace the actions that you don't like doing with the actions you do like doing. Double DX, double DY. I need a double DZ in here. Is that the problem? That's not the problem. Let's go ahead and clear this, and let's just clear it again, and let's make it. Okay, so it's saying error duplicate parameter name. Oh, duplicate parameter name. What is your problem? Par, data, out, x dimension, y dimension, z dimension, double dx, double dy, double dz. Error undefined, identify a grid. That's because I forgot a dim3 here. And we need it there. And we also need it down here. And let's go ahead and make that. Error type double 2 star is incompatible type doubled. What's 23? G size is undefined. I also forgot an int there. Oh my gosh, I'm an idiot. I've gotten so used to writing Julia code that my C++ is just crap. Okay, let's keep going. Write this, go over here, make that. The next error should be double 2, so this is gonna be on line 23. Energy sum. Okay, that's because energy sum must be for double values. So let's go ahead and open up another terminal here, cd projects GPUE. LS over here. And let's just go into VI source and kernels, I believe, and sum. Double 2 in 1, double 2 in 2, double output. I see the problem. I need just double 2 in, double 2. Let's just create a new one just called sum. All right. Global. I don't know where to put it exactly, but you know, I put these guys here, so we're just gonna do global, and we're just gonna call it void sum, and it's gonna take in a double 2 value. It's gonna be in 1, in 1, then double 2, 2 star in 2, and then we're just gonna do double 2 star out. But again, as far as finding motivation is concerned, it's hard. Like, no, I'm not trying to like beat around the bush here. It's hard. You just kind of have to find the right people who enjoy doing things that you also enjoy doing. And if you can do that, I think it's, you know, I think it's something that most people can find fulfillment. Like, people can find fulfilling things to do that also are useful, I guess, waste of time. I think I can do this. Yeah, let's see what happens. So now we're just going to do sum here instead of energy sum. Let's make that. I don't know what I'm doing anymore. All right, didn't work. Let's go to VI kernels, source kernels.cu. Let's just do sum. Void sum. So it should just, we should add all the x components and y components. So this is gonna be .x. Let's see, .x, yank and paste, and then we have to do the .y's. Yep, .y. Okay, make that. Around other people, let's see, like physics, comp sci, math students, I get really into talking about subjects that I'm out of my depth in, but I still enjoy discussing. Yet it's hard to break out of the unsatisfying time waster hobbies. Coding is really gratifying, yet it's easy to just put off in exchange for some other kind of instant dopamine hobby. Oh, that's because I forgot to put this in the include file. VI include kernels, sum, void energy sum. So I think I'm just gonna put it down here because it's very much the same. This should be energy sum. Yeah, I don't know. I mean, depending on who you are and how you work, I think, I don't know. I think it's pretty easy to find things that are enjoyable and fulfilling, you know? And again, wasting a little bit of time on YouTube or Twitch or whatever, it's not a bad thing. I mean, it's okay. It's perfectly fine to just take your time and enjoy life a bit. And if you're enjoying life as just watching a YouTube video, I think that's perfectly fine, I believe. Double 2 in, double 2 in, double 2 out. What? Oh, I must have already fixed it. Okay, whatever. Let's go here and make that. I'll talk about that in just a second. Let me go ahead and get this guy building. Is it? It shouldn't be building. I missed a semicolon. You can't build. Don't give me that. 40. Yep. Okay. Let's see. Identify threads undefined. Let's go ahead and make that guy, and hopefully it works. Now 54. Oh, I see the problem. I need to change this again to sum. Okay, make that. Okay, so now the Laplacian function should be in the code. So now it's up to us to fix the energy function. So I think what I might do is I might commit one more time, just because now we have the Laplacian in, and I kind of feel like, you know, let's go ahead and add these in too. Git status. Git add include, 1 second, star, source star, git commit, -m, added Laplacian functions, 1 second. Okay, nice. I just got a message on Slack. Okay, good. I mean, this is technically work time for me, so I need to make sure that I'm not missing any meetings or anything like that. Okay, so we're going to, now that that's working, I think we're just gonna try to do the derivative, the double derivative as expected. So let's go ahead, so let's go ahead and do VI source split up. Let's go to energy calc here. And we have all this guy up here. I think if we just don't deal with the Fourier transforms, I think we can do this. So I'm just going to go ahead and remove all this QFFT handle stuff. We have part of B value D rotating. We don't need the renormalization. Wave function K. I think we could probably even get away with not having a wave function K. We could probably just have, yeah, I think we can get away with not having wave function K here. Okay, so we have energy R, energy K, so we don't have to have this guy anymore. We have energy here. Then we're going to do CUDA malloc energy. Yep, seems fine. Vector conjugate. Yep. Now we don't need this guy anymore, and instead we're going to change this. Scalar molt, vector multiplication. We need this vector multiplication, but I think this is going to change to a C molt. Because it should be a complex multiplication now. And we don't need a CUDA free anymore because we'll be keeping the the wave function K, or the energy K. QFFT exec, we don't need that. Scalar molt, we don't need that. We just need a C molt here. Wave function C, yep, so this should be what we need. So let's see, what do we have here? I guess we're just multiplying by K. Yeah, this is it. So let's go ahead and do it. So it's going to be Laplacian. We just defined this, so grid threads. And what we're going to do is we're going to read in the wave function. And we're going to output the energy K. Then we just have to read in X dimension, Y dimension, Z dimension, dx, dy, and dz. Except we have to do a small scale modification here. So this is going to be wave function K, energy K. Okay, so let's go ahead and do one more thing in here. So it's going to be if dim num is equal to 2. We're going to have to do something slightly different than if dim num is equal to 3. Unfortunately, I'm running out of space, so I'm just going to pop these guys onto the next line. Okay, and then if dim num is equal to... Oh, I don't have a 1D, do I? Dang, I'm going to have to do 1D Laplacian too. Okay, that's okay. So we'll say if dim num is equal to 2. So we're going to do yank 1, 2, 3, 4. Yank. We're going to paste it down here. We're going to paste another one up here. And we're just going to do dim num equals 1, 2, and 3. So let's go ahead and get this guys done. So okay. So if it's 1 dimension, we're just going to need X dimension. And then we're just going to need a dx. D $, and it's going to be a dx. Okay. This is going to be here. And then for this one, we're going to need, I guess it's just going to be y dim. And then it's just going to be dx and dy. Something like this. dd there, dd there. And then for 3D, that should be correct. Okay. I'll be right back, guys. Give me just a second. Okay, hey, let's see. Right, other people like physics. Yeah. Okay, so now I have to implement one more Laplacian function. So let's go ahead and do that right now. Let's see, we're going to go into, where was it before? I believe it's in operators. .cu. So let's go to vi source, operators, and let's go ahead and implement the 1D Laplacian. So I'm just going to grab this guy. 1D Laplacian is rather straightforward. It's just basically d squared, but that's okay. So Laplacian here, we are going to read in x dim, y dim here. So it should just be x dim, x dim. It should be then double dx. There. dd there. Okay, we don't have, G size is just going to be X dimension. Don't need anything complicated there. And then we stop at some here. There. And then we free the temp derivative. Now, do we even need the temp derivative in this case? So we're going to copy the temp derivative to out. We might not need that. We don't need a sum, definitely. So we can just derive data onto out. And then we can do the same thing here. Okay, nice. So CUDA-malloc here, we don't need that anymore or that anymore. That should be it for the 1D Laplacian, I think. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So D15D. And I'm just going to paste this down under the 2D one. Just because we did 3D, 2D, then 1D. So let's just put these in the right order. Okay, nice. I'm going to DD here. And now let's go into VI include operators.ch. Let's look for Laplacian. What? I'm confused. How did VI energy check? Let's go VI source energy. Oh, I'm sorry, it's going to be split up.cu. Let's go to energy calc. I'm using the Laplacian here. Wow. It's not in the include file. What's going on? Oh, man. Oh, I shouldn't have committed. I thought we were done. Identify par as undefined. Okay. Let's go. Let's fix all these guys then. Let's go to VI source operators. Laplacian grid par should be fine. Oh, but we're not reading in curl 2D, curl 3D, curl 3DX. Yeah, we have grid ampersand par all here, so that should be fine. It's gonna say 61. dim3 grid equals par.grid. What? Aha. Okay, identifier temp derivative is undefined. Let's go to 68. Yeah, so this should be, we don't need a copy anymore. We can just directly, and then we don't need a CUDA free. Make. Okay, seems to build, except for the fact that Laplacian is not found. So let's go ahead and add those in there. So we're going to go into VI include operators.h, and here we're going to go VI source operators.h. Let's go down to, you know what, we'll just add it up here. I don't mind. So we're just going to do void Laplacian. There. Add there. And we're just going to add the other guys in here too. Okay, scroll down a bit. Add this in there. Oh no. 1 second. Void. So these are all Laplacian functions. Okay. I don't care so much about that. Quit here, over here, make that. Oh, I see why I committed before. Because I didn't necessarily want to update the energy until after the Laplacian functions were in. Laplacian is undefined, split up to 80. Okay, let's go into split up. And am I reading in operators? No, what am I reading in? Lattice, edge, manip, vort. Yeah, okay, I guess I'm just gonna have to read in operators, aren't I? I could just have this in kernels. But these aren't kernels, so I don't think that's fair. Identifier Laplacian is undefined. Split up, double, let's see, 290. CMult grid energy K. Argument of type double star is... Ah, I see. So I've got to do... How do I do the multiplication with V? Is it vector mult? Ah, okay, so I'll just do vec mult. Okay, so now I have to figure out this Laplacian nonsense. one here. Operators.h, it is included. Make clean. Make J4. And again, guys, if you have questions, comments, concerns, just feel free to ask. I don't have too much more time that I'm able to stream today because I have to head in soon. I'm just trying to get this Laplacian guy done. Energy L was declared, but oh, I see the problem because it's within an if statement that all that is done. Okay, that's fair. Then in that case, I could probably... anyway, let's get this Laplacian stuff, guys. Laplacian is undefined. Did I misspell it? Laplacian. Operators? Laplacian. Seems fine. What? Grid threads. Void. Oh ho. I see. This is just a host function. We don't need grid and threads in there. What was I thinking? Oh, okay. Write this, go over here, quit there, make that. You're still undefined. How are you still undefined, dog? What is the problem? Okay, let's go here. 281. I know you're undefined here, but I'm reading in operators.h. I include operators.h. VI source operators. They're there. I don't understand. Include operators.h. Kernels dynamic.h. Huh. I don't understand where they'd go. Quit here. Identifier Laplacian is undefined, but they are defined. They're in the header file. Include operators.h. Evolution.h. Where am I? I'm on splitop.h. I could put this in kernels. I don't mind. I mean, they're host kernels. It's fine. Do we have other host kernels in kernels? VI source kernels. Host. I mean, they're always host and device, I believe. Do we have any? Yeah, I don't think we even have any. Okay. Where would it go? Why are you having trouble reading that in, dog? 1 second, I got another notification on Slack. Okay, nice. Okay. So... Okay. Why can I not find the Laplacian? It says, files GPUE. Maybe I need to CMake one more time? I don't know. Okay. It's going to vi split up dot oh, that's binary file. Vi source split up dot cu include operators dot h. No idea. Yeah, of course that doesn't exist. VI include operators.h. Void Laplacian. They're there. I don't understand what the problem is. We have identifier Laplacian is undefined. Says void Laplacian, double curl 2D. I can call the curl 2D function without any problem, I believe. Yeah, this is definitely where it belongs, though. So why are you undefined? Huh. Make... Put it in the header file. I updated... Include ds.h, constants.h, unordered map. Void Laplacian. Laplacian. Oh, it's a spelling error. Oh my gosh. This whole time. It's a spelling error. Bah. Okay, well, at least that's found. Let's keep going. Plossian. Make that. Should build. Okay, and hopefully I'm going to run the unit tests and we're going to see if the energy works. If the energy works with this... what is your problem? Double 2-star, double 2-star, int double. Double 2-star? Aha. Okay. VI source split up. Laplacian. I need to read in par. For all of these guys. Okay. Again, guys, I mean, chat's kind of quiet. It doesn't... It's cool. I mean... if you guys have questions or you want to talk about something, just feel free to comment. I apologize if I accidentally shut down a previous conversation or something. Okay. This guy's built. Let's see what happens. That's what I figured. Crap. Yeah, that energy computation is wrong. Which means I did something else wrong. No, I don't want to show that. Okay, so here we have the energy here. I added in the Laplacian here, so we did the vector conjugate. Let me just check to see what we have here. So we have dim num equals 1. Then we just perform energy k. Laplacian of energy k, x dimension, y dimension. Then we do a vector multiplication of energy k and k. Yep, then we multiply it by... And we multiply it by... Wait a minute. I think maybe... Let's comment this out. No, crap, that's way bad. Ah, darn. Okay. I see. That particular... We were multiplying by k squared because that was, you know, we were using derivatives with Fourier transforms. I can just Google this. Okay. I mean, fair enough. Fourier transform derivative. You multiply in Fourier space and then you... yeah, you can perform a derivative with Fourier transform. And that's what we were doing before. Let's look for derivative. Time derivative is just going to be the Fourier transform of the derivative of x. Let's see. Ah, crap. The derivative property. Yeah, so that's what we were doing before. We were Fourier transforming forward, multiplying by k. Okay, but maybe we're okay. Let me revert back to what we had before. So let's just go ahead and do quit. Get checkout. Let's do get stash first. And now we're gonna do get checkout source split up .cu. We're gonna make that. Actually, okay. Get stash apply because I want some of these changes. And then we do get checkout. What am I doing? Checkout source and then split up. That's you. We're gonna do make, and then these tests should pass. I'm just gonna run this. So since we have this now, I think I'm just gonna head into work and I'm gonna run this and we're gonna see what happens. So we have the derivative function in there. Should be good to go. And yeah, I think that's a good place to stop for now. So let's go ahead and run GPUE-U. And this will be where I stop for now. Just make sure the unit tests are passing, and they seem to be, so I'm not too worried about this. So let's do get status one more time. Get add, include, star, source, star, get push, origin, energy fix. Get commit, sorry about that. Dash M, fixing Laplacian. Functions. Okay, get push. origin energy fix. Okay, so I think that's gonna be it for now. I'm gonna just, I guess, get an early lunch, head back into work, and that will be it. So thanks guys so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simulaos, where we will work on domain coloring, again, tomorrow morning from 5 to 7. Thanks guys, and I'll see you next time. Bye guys.